Hey everybody, Dr. A here, and in this video we're going to be exploring an example dealing with distributed loading. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
So in this example, we're again exploring the idea of computing the total equivalent load. So again, I'm gonna have a beam here. It doesn't really matter what the geometry of the beam is necessarily. What we really care about is what the geometry of the loading, the distributed loading is on a member. Okay, so here we're gonna have, again, I'm gonna have a W axis here, and I'm gonna have an X axis here. So that's our origin, and then my load in this case is gonna be something like this. Okay, now you may be noticing that this looks kind of curved. So here I'm giving you a function. I'm going to say W is a function of X equals 2X squared. Okay, and then the length here is going to be spread out over 10 feet, and my units for W as a function of X, my units are going to be in pounds per foot. Okay, so here we go. Let's go ahead and get started. We're going to go ahead and say solution. Now, the first thing I want you to notice is the distributed load is quadratic. Okay, it's quadratic. So notice that it's the graph, or the shape of this, is parabolic, right? Remember, the graph of a quadratic function is a parabola. So this is literally a parabolic segment. Okay, it's curved, and look at that. We have the function right there, 2x squared. Okay, now and we say it's carrying units of pounds per foot. It's spread out over 10 feet. So guess what we do? We take the integral. Now, can we compute the equivalent load using simple geometric areas by find the area under this curve? Not really. That's the whole idea of an integral. If you have a shape that is not a convenient shape, like a rectangle or a circle or a triangle or something like that, you take an integral. So in this case, we have to take the integral form because we really, we really don't have a convenient ready-made formula for the area of a parabolic shape. So we're going to say F equals integral, of course, 0 to L, W is a function of X dx. That's our integral form. And we're going to say the equivalent force is equal to the integral from 0 to 10 feet of 2x squared dx. Okay, and here we just take the integral, and this is a simple polynomial, so hopefully you can do this in your head. You remember we raise it a power, divide by the new power, so we have 2/3 x cubed evaluated from 0 to 10 feet. So again, we do upper limit minus lower limit. And so when we cube that 10, we get 1,000, right? And so we will end up with, let's see, 10 cubed times 2 divided by 3. So we end up with 667 pounds as our equivalent load, and it is pointing down. Now, here's where you kind of have to be careful, okay? In this particular case, this is where we kind of have a discussion about the sign, SIGN. All right, in this particular case, I was given a function that was 2x squared. So, of course, the plot of that function is given as this little parabolic segment here. Well, notice the coefficient in front of the x squared term is positive. So you remember from calculus, what does that mean about this graph? That means that this graph should be concave up since my coefficient is positive, and it is. Clearly, this is drawn as concave up, so this function matches with the shape of this curve. But again, it still represents a physical loading which is acting downward. So again, that's why I prefer to take the positive version of this, because the positive 2x squared does correspond with a concave up shape of this load distribution. And then at the end of it all, I put a downward point or a downward little vector indicating that, hey, this loading is acting downward. All right, and that's it for this. That's it for this example.